Dear viewers, I welcome you all for the yet another lecture session on the topic electromagnetic radiation. As you all know, stationary electric charges produce electric field, whereas moving electric charges produce both electric and magnetic fields. Repeating changes in these fields produce what we call electromagnetic radiation. The electromagnetic radiation transports energy from point to point. This radiation propagates through space at about 186,000 miles per second. That is, it travels the speed of light. Indeed, light is one form of the electromagnetic radiation. Some other forms of electromagnetic radiations are X-rays, microwaves, infrared radiation, AM and FM radio waves, and ultraviolet radiation. The properties of electromagnetic radiation depend strongly on its frequency. The frequency is the rate at which the radiating electromagnetic field is oscillating. The frequencies of electromagnetic radiation are given in hertz. As the radiation propagates at a given frequency, it has an associated wavelength, that is, the distance between the successive crests or successive troughs. That is nothing but the wavelength. And these wavelengths are given in terms of or given in meters. Since all electromagnetic radiation travels at the same speed, the number of crests passing a given point in a space in a given unit of time varies with the wavelength. For example, 10 waves of wavelength 10 meters will pass by a point in the same length of time. It would take one wave of wavelength 100 meters. Since all forms of electromagnetic energy travel at the speed of light, the wavelength equals the speed of light divided by the frequency of oscillation. So in the diagram given below, you could see C is equal to lambda into F, where C is the speed of the light and lambda is the wavelength and F is the frequency. And this one property, you should know the relationship between wavelength and frequency of electromagnetic field. Next, coming to the electromagnetic spectrum, a distribution of the continuum of all radiant energies can be plotted either as a function of wavelength or frequency in a chart known as electromagnetic spectrum. And this electromagnetic spectrum ranges from shorter wavelengths including X-rays and gamma rays to longer wavelengths that is microwaves and radio waves. And these electromagnetic spectrum is the range of all possible frequencies of electromagnetic radiation. And this EMR extends over a wide range of energies or wavelengths or frequencies. We can have a look at this diagram, where this diagram represents the various electromagnetic radiations. You can see here this are radio waves followed by infrared. Next comes the visible radiations, ultraviolet, X-rays and gamma rays. So you can see the wavelength distribution of these wavelength ranges in terms of nanometers. And in short, how you can remember in short, you can remember this way, that if you uh, consider the wavelength will start, okay, when this part, beyond this part, this visible light radiations, the wavelength will increase with decrease in frequency. Since you have seen C is equal to nu lambda, wavelength increases with a decrease in frequency. Here, the wavelength decreases with increase in frequency. And you could see here that this is a visible light radiation. And very clearly with the pictorial representation you could see from the visible light from this median point, from this midpoint you can see longer wavelength. Longer wavelength is high wavelength, it means it's low frequency, radio frequencies or low frequencies with low energy. Similarly, X-rays, high frequency, high energy X-rays, gamma rays, uh, high frequency, high energy, but shorter wave. I believe you could able to understand the electromagnetic spectrum in detail.